Okay, so hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Materials Science program from the University of Ontario Institute of Technology. So I also took my Bachelor's of Science at this institution as well in pharmaceutical chemistry. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you had any problems with homework or tutoring, then check out the links in the description below. So now I'm just going to get started on our set of questions for today's session. Okay, so question number 1 starts off pretty broad, but basically they are asking, what are functional groups? Functional groups. So this is one of the first things you learn about when we're talking about chemistry or organic chemistry in general. And basically they are like substituents that can make your molecules unique. And they also affect how they will react in a chemical reaction. So there's a lot of different functional groups. I'm just going to get started and write down all of the main ones, and yeah, I'll just write them all down. So the most basic one in organic chemistry is just called an alkane bond. And this just represents a single bond between two carbon atoms. You can have an alkene bond, which shows that there is a double bond between carbon atoms. And lastly, there is an alkyne, which, as you can guess, represents a triple bond between two carbon atoms. You can have alkyl halides. So this is when your carbon is connected to like a bromine or like a chlorine, any of the different halogens. And I will from now on denote R as kind of like the rest of the chain. So it's just a way for chemists to, if they don't want to write out the whole carbon group, you can just denote it as R. After alkyl halides, you could have alcohols. So again, I'm just going to do R just to signify another carbon group. And alcohols are when you have an OH. Similarly, you can have a thiol, where instead of oxygen, it's sulfur. You can have an ether group. So I'm going to write it like that. In a way, me and my friends remembered ether groups is that there's like a carbon on either side of the oxygen. So that's just how we try to memorize these different times groups. That's what an ether is. For amine, this is when you have a nitrogen involved. So the simplest amine is just like an NH2 group or NH3. All right, NH3. And you can have a ketone. I'm going to draw it like this. And this is when you have a double bonded oxygen in the middle of two carbons or carbon groups. So another way that we remembered this is that you put the key in the middle of two like R groups, so ketone. And what's similar to ketones are aldehydes. So again, there is a double bonded oxygen, but the only difference is that it's at the end of a carbon group. So instead of being bonded with two carbons, it's bonded with a carbon group and a hydrogen. You can have carboxylic acids. So basically, this is like putting together an aldehyde and an alcohol, like put together. And you get this group right here, where it's like a double bonded oxygen and then an OH. And then what's similar to carboxylic acids are carboxylic esters. So as you can guess, this is similar to carboxylic acid, except instead of it being at the end, it's in the middle of two carbon groups. And you can have a nitrile. So this is when we have like a carbon that's triple bonded to a nitrogen. And then lastly, you can have like a carboxylic amide. And as you can guess, it's kind of similar like a carboxylic acid, where you have a double bonded O, but instead of the alcohol group, it's gonna be an amide at the end. So these are all the different main functional groups that you can have in an organic molecule. Let's see our answer from the junior tutor. Functional groups are specific substituents that distinguish the chemical reaction of one molecule from the other. In organic chemistry, the molecules with the same functional groups will undergo a similar chemical reaction. Examples of functional groups include carboxyl, aldehyde, ketone, etc. The figure below shows the common functional groups and their structures. Okay, so you can just see a more detailed version of what I tried to show. They have examples of alkanes, alkenes, and how you can have like a double bond at the end there, not just in the middle. Alkynes can be in the middle or at the end. Alkyl halides, they showed both bromine and chlorine as an example. Alcohols, thiols, esters, which is kind of cool. They show how you can have like a benzyl ring as an ether. Your amines, so this can be like a secondary amine or a tertiary amine. So here they showed a primary and a secondary amine. The ketone, so as long as it's in the middle of two different carbon groups, that's your ketone. For aldehyde, you have the double bonded oxygen, but instead of having another carbon group here, it's at the end, so we show a hydrogen. Carboxylic acid, carboxylic ester, carboxylic amide, and then a nitrile. So this solution is correct. Okay, so let's do question number 2. What are the steps involved in calculating the empirical formula of a compound? So I'm gonna do like a sample like example, and I'm just gonna do an example of how you would calculate an empirical formula, and then I'll also like talk about the different steps. So I'll write down the steps first. Basically, step 1, you want to find the moles of each element. Step 2, you want to divide by your smallest mole value. Step 3, so that when it's in its smallest mole value form, you want to make sure everything is in whole numbers. So you want to convert to whole numbers. So this will make more sense when I do an example at the bottom. So I'm going to do an example with ethyl butyrate. So basically when they give you an empirical formula question, they give you like the mass of the total compound, and then they also give you like the mass of carbon dioxide or water that was expelled when this compound was combusted. For example, they'll give the mass of ethyl butyrate. Like let's say it is 2.78 times 10 to the negative 3 grams. And they'll give you the mass of carbon dioxide and also the mass of water. So let's say the mass of carbon dioxide was equal to 6.32 times 10 to the negative 3 grams. Step 1 says to find the moles of each element. So I'm going to find the number of moles of carbon, of the carbon dioxide. And to do that, we divide by its molar mass, which is 44 grams per mole, to get number of moles, which is 1.4 times 10 to the negative 4 moles of CO2. And then to find out how many moles of each element, since there is 1 mole of carbon for every mole of CO2, that's how you would find the moles of carbon. And then to find the mass of carbon, I'm going to multiply by its atomic mass to get a final value of 1.72 times 10 to the negative 3 grams of carbon. So let's do the same thing with the water. So let's say they give you a mass of water that was expelled during the combustion, and they give you like 2.58 times 10 to the negative grams. You would divide by water's molar mass, which is 18 grams per mole, to get the number of moles of water, which is also 1.4 times 10 to the negative 4 moles of water. To find out the moles of hydrogen, there are 2 moles of hydrogen in every 1 mole of water. And then to find out the mass of hydrogen, I'm going to multiply hydrogen's molar mass, and then I get 2.9 times 10 to the negative 4 grams of hydrogen. To find the mass of oxygen that's left over, let me use a different color. Find the mass of oxygen. It's going to be our total mass, which is the 2.78 times 10 to the negative 3. And then I'm going to minus the grams of carbon and hydrogen that we found in the first part of the question. So basically, this is because we know that this compound only contains carbon, hydrogen, and oxygen. We can do this part. And you get 7.7 times 10 to the negative 4 grams of oxygen. So next, I am just going to find the moles of each element. So the first part was asking, I found all the different masses, so now I'm actually just going to find the moles of each atom. So for carbon, it was 1.72 times 10 to the negative 3 grams. I'm going to divide it by the molar mass of carbon, which is 12 grams per mole, and I get 1.43 times 10 to the negative 4 mole of carbon. For hydrogen, it's 2.9 times 10 to the negative 4 grams over 1.01 grams per mole. And we get 2.87 times 10 to the negative 4 moles of hydrogen. And then I'm going to do oxygen on the next page. For oxygen, we had 7.7 times 10 to the negative 4 grams oxygen divided by its molar mass, which is 16 grams per mole. And you get 4.81 times 10 to the negative 5 moles of oxygen. So now I'm going to write out the empirical formula just by using these mole values that we found. So for carbon, it was the 1.43 times 10 to the negative 4. For hydrogen, it was 2.87 times 10 to the negative 4. And then for oxygen, it is 4.81 times 10 to the negative 5. So since the smallest value here is the oxygen, we are going to divide all these values by the smallest mole value. So that was step 2 in the steps. And this gives us C3H6O. So since everything is already in whole values, this would be your empirical formula. So let's see what our junior tutor said. In definition, the empirical formula gives us an idea of the ratio of the relative atoms in the compound. For example, H2O only contains 2 atoms of hydrogen and 1 atom of oxygen. We can also interpret it as 1 mole of H2O contains 2 mole of hydrogen and 1 mole of oxygen. So they did So this is if you don't have any mass and you need to calculate an empirical formula, you can assume 100 grams of a sample of the compound, and that's an easy way to convert from percentage to grams. So like what they said, using the element's molar mass, convert the grams of each element to moles. Convert the resulting moles to a whole number ratio by dividing the moles of each element by whichever the mole from step 2 is the smallest. So this is similar to our example. We divided it by oxygen's moles. After converting, the empirical formula can be written with the moles as the subscript of each element. In other cases, one or more moles from step 3 will not be converted to whole numbers. Multiply each of the moles by the smallest whole number that will convert each into a whole number. And then you can find out your empirical formula. So they have an example of their own. They say an unknown compound contains 69.94% iron and 30.06% oxygen. Find the empirical formula. So this is when you would convert by assuming 100 grams of the sample, we can convert the percentage to grams. And then they found the number of moles of each element divided by the smallest value obtained. So for iron, that was the smallest amount of moles, so you get 1. For oxygen, when you divide 1.87 by 1.25, you get 1.5. So you can see that there's a decimal involved. So that's why we need to multiply both by 2 to convert it to a whole number. So they get an empirical formula of Fe2O3. So this solution is correct. Okay, so let's look at question number 3. What is oxidation? So when you have an oxidation reaction, this is when there is a loss of electrons for your atom. It's also when you have an oxidation number, then an oxidation reaction. And the oxidation number of the element or the compound will increase. So the opposite of an oxidation reaction is a reduction reaction. And as you can guess, this is when you have gain of electrons. And its oxidation number will decrease. So there's different ways people try to remember which one loses electrons and which one gains electrons. So one of them is by using oil rig. So this means like oxidation is losing electrons. Reduction is gaining another one that people use is like Leo-Gur. Doesn't really make as much sense as oil rig, but it's just another way. So this is like losing electrons is oxidation. Gaining electrons is reduction. So whichever one helps you. I think I used oil rig when I was a student. I'll just also write down like an example of an oxidation reaction. So let's say you have lead solid plus like chlorine gives so this is an example of an oxidation reaction. If we base it on the lead, it starts off with an oxidation number of 0. The chlorine has a -1 oxidation number. When it is in a compound with the chlorine, its oxidation number is +2, and that's because each chlorine has a -1 charge. So you can see that the electrons were lost, and this is an example of an oxidation reaction. If I wanted to write out a reduction reaction, let's say I had silver chloride. So when you have a reduction reaction, your electrons are the reactants. So that shows that there is a gain of electrons. So let's look at the oxidation numbers after I balance. We can look at the oxidation number of the silver. It started off, let me just balance this. It started off with a +1 oxidation number since it's bonded with a chlorine, and since the compound is neutral, shows that it has a +1 oxidation number. When it gains the electrons, the oxidation number decreases to 0. This chlorine gas. And that's an example of a reduction reaction. So in this case, the silver got reduced and the chlorine got oxidized. Let's see the answer from our junior tutor. An oxidation reaction is the half reaction that involves the loss of electrons. We say half reaction because oxidation always occurs with reduction. Another way to frame this is that oxidation occurs to a species when there is an increase in its oxidation state or oxidation. For example, given the net reaction below, they have copper solid plus silver 2 plus makes copper 2 plus silver solid. We can split the reaction into its half reactions. This would be copper solid makes copper 2 plus 2 electrons, or silver 2 plus 2 electrons makes silver solid. We can say the copper undergoes oxidation or is oxidized because the species lost 2 electrons and that its oxidation number increased from 0 to +2. This solution is correct. I'll add the oil rig and Leo Gur thing just to help out. Okay, so this solution was correct. And I'll move on to question number 4, which only asks, what is potassium permanganate? So just generally speaking, potassium permanganate is KMnO4. So let me break this up into its ions so you can see where the name comes from. So this is a potassium ion. And then this is a permanganate ion. Permanganate ion. I'll also draw out its structure. So it's when you have manganese that is bonded with 4 oxygens and a single potassium. Let's see what our junior tutor said. It looks like they have a lot about it. Potassium permanganate is a common chemical compound that combines manganese oxide or with potassium hydroxide. However, it's easier to be understood as a combination of potassium ion and permanganate ion. And they draw out the Lewis structure. It appears as a purplish colored crystalline solid, non-combustible, but accelerates the burning of combustible material. If the combustible material is finely divided, the mixture may be explosive, so you have to be careful with this. Contact with liquid combustible materials may result in spontaneous ignition. So make sure you read your MSDS when working with potassium permanganate. It was first developed as a disinfectant. Then it was widely used to treat a variety of skin conditions, including fungal infections. It's useful for detection, identification, analysis of chemical biology. I can't read. Or pathologic processes of condition because of its chemical properties. Indicators are substances that change in physical appearance when subjected into different chemical reactions. Okay. The compound is also used for treatment of fish diseases, conveniently cures bacterial gill infections and skin ulcers. Lastly, it is also used for water treatment. So potassium permanganate is useful for like a lot of different things. But this solution is correct. Very informative answer. I learned a thing or two just by reading that solution. Okay, so let's look at question number 5. How do you express 275 millimeters of mercury in ATM and Pascal? So I'm going to use the conversion factor where 1 ATM is equal to 760 millimeters of mercury. So if you have 275 millimeters of mercury, I'm going to multiply by the conversion factor. So whatever units I'm looking for will be on top. The units I'm trying to get rid of will be in the denominator. And then if we divide, we end up getting 0.36 ATM. So this is what our junior tutor did as well. Alright, the pascals. In terms of pascals, since we already got the value of 275 millimeters of mercury in terms of ATM, we use the conversion factor 1 ATM is equal to 101.325 kilopascals. Okay, so this solution is correct. Okay, so now we can do question number 6. How do you find the ideal gas constant? So the ideal gas constant is denoted as R. So the way I'm going to try to find the constant is by using the ideal gas law. PV equals nRT. So we're looking for R. P stands for pressure. So ideally, pressure is 1 atm. V is volume. So I'm going to use 22.4 liters, which is defined as the molar volume. So N is number of moles. So ideally it's just 1. We're looking for R, and T is temperature. So for this temperature value, I'm going to use the 273.15 Kelvin. So we don't use room temperature. We use the 273.15 since this is defined as the 0 point on the Kelvin scale. Okay, so now I'm just going to rewrite this equation and try to solve for R. So R is equal to PV divided by NT. So 1 atm times 22.4 liters divided by 1 mole times 273.15 Kelvin gives you 0.08205, and then the units are liters times atm over mole times Kelvin. Let's see the answer from our junior tutor. Definition of PV equals nRT can be found in the molar volume of gas at standard temperature and pressure. The standard pressure is 1 atm, molar volume is 22.4, and the temperature is at 273 Kelvin. Okay, so they got the same value. So another thing you want to be careful with when using the ideal gas constant is that these are it can be given in different units. So it can also be 8.314 depending on the units they give you, but this is the most widely used R value. Okay, so let's check out question number 7. What is electron affinity? So electron affinity is like the energy change when an electron is accepted by an atom. So another way we can define it is that it's basically the energy needed to remove an electron. So our junior tutor said it's the negative of the energy change that occurs when an electron is accepted by an atom in the gaseous state to form an anion. Since electron affinity is a form of energy, the unit is kilojoules per mole. Another way to look at electron affinity is that it is the amount of energy needed to remove an electron from an anion. The higher the electron affinity of an element, the more likely it is to accept an electron. This solution is correct. Okay, so what is an example of entropy from everyday life? Okay, so first I'll write down what entropy is. Basically, it measures like the randomness of a system. Entropy is also a spontaneous reaction. I'll also give some common examples. So one example is the air leaving a balloon. So let's say we have a red balloon. It's nicely inflated and it contains on the inside these air molecules. So the only reason why they are in there is because someone blew them into the balloon and then sealed it. But ideally, you can just try to picture it. There's a lot of different air molecules that are pushing together inside this balloon, and they really don't want to stay there. Let's say someone came and like just hit it with like a needle. Okay, this is supposed to be like a sharp dagger thing. And you break the balloon. Let me try to draw that. After the balloon is broken, puncture a hole in it, all of these air molecules, this is me drawing air molecules leaving, they leave the balloon. So this is a spontaneous reaction. It's also an example of an increase in entropy. So another like common example is when you mix like pure substances together. Let's say you have like A and B. I'll write A. You'll have just a nice ordered. Wait. Let me make it look good. A nicely ordered A pure substance. And you also have an ordered like B substance. If you were to like mix them up, this is an increase in entropy since it increases like the messiness of the system. Let me just draw it like that. And just another simple example is when you dissolve sugar in water. There is an increase in entropy. Okay, so I think that's enough examples. Let's see what our junior tutor said. Entropy is the measure of the randomness of a system. The total entropy of the universe is always increasing due to the spontaneous distribution of energy. We see different examples of changes in entropy in our everyday lives. Change in entropy can be observed from the following phenomenon. Melting of ice in the Arctic region. So this is an increase in entropy because of the change of state from solid to liquid. Burning of wood. This is releasing of energy and gases such as CO2 and water vapor. Rusting of iron. So this releases energy as a result of oxidation. You can have the dissolution of salts and sugar in water. So this is like what I said, the increase in entropy because of breaking the OH bonds. And finally, storing sugar molecules during the photosynthesis of plants. So this is an example of a decrease in entropy since carbon and water molecules are combined into more ordered sugar molecules. So when you have carbon and the water molecules combined, this requires energy. So therefore this reaction is not spontaneous since it requires energy. And that is actually the energy that you get from the sun in photosynthesis. Let me just say that this solution is correct. Okay, so let's check out question number 9. How do you convert mph, miles per hour, to meters per second? So let me write mph as miles over hour. To convert to meters per second, first I'll look at the seconds portion. So if you wanted to convert from hours to second, I like to put whatever I want to cancel out at the top if hours is at the bottom here. So there's for 1 hour, this is the same as 3,600 seconds. So this is how you would cancel out hours. To convert miles to meters, I'm going to multiply by 1,609 meters per mile. So that's the conversion factor there. If I were to simplify the units, you get 0.447 meters per second. So let's see the answer from our junior tutor. To convert the given units of speed, we just need to convert the length and time element of the units. The conversion factor is 1 hour to 3,600 seconds and 1 mile is 1,609 meters. Say you have a car driving at 1 mile per hour. To get the speed in meters per second, we use the conversion factors given. So they did the same conversion factors I did as well. Thus, the speed of the car in meters per second is 0.447 meters per second. So basically, you just multiply by 0.447. Okay, so let's look at question number 10. So this is similar to the other ideal gas law question I had, but this time they're just asking what is the gas law, or what gas law is PV equals nRT. So this gas law is called, this is derived from the kinetic molecular theory, which basically has different assumptions. So this theory is based on the assumption that your gas molecules are constantly moving. You want to also assume that the space in between gas molecules is greater than the molecules themselves. This is also assuming that kinetic energy is determined by temperature. And lastly, assuming that all collisions are elastic. So PV equals nRT. It comes from basically combining all of the different gas laws, such as Boyle's, Charles's, and Avogadro's. So I already went over what each of the different variables means, but I'll just say it briefly again. It's pressure times volume is equal to number of moles times the gas constant R times temperature. So let's see what our junior tutor said. Ideal gas law is a simplified equation that was derived using the assumptions of the kinetic molecular theory. 1. The space between gas molecules is much larger than the molecules themselves. 2. Gas molecules are in constant random motion. 3. The average kinetic energy is determined solely by the temperature. Note this statement implies that all molecules have the same kinetic energy at a given temperature, regardless of their mass. 4. All collisions between gas molecules and between the molecules and the walls of the container are perfectly elastic. No energy is lost because of the collision. Ideal gas law combines all the gas laws, Boyle's, Charles, and Avogadro's, and is expressed as PV equals nRT. Value of the gas constant R differs depending on the unit of measurement of other parameters. Table below lists all the possible values of R. So this is what I mentioned earlier, like depending on what a question like gives you, if they give you a value in joules or in meters cubed, like the R value will change depending on what the units are. So this 0.0821, this is the same thing that I calculated in the previous question, and it is in liters times ATM over mole times Kelvin. 8.3145 is another common R value that you may have to deal with, and its values are in joules over mole times Kelvin. And then the last two, they aren't commonly used, but basically it's 8.2057, and the units are meters cubed times ATM over mole K. And then the last one is 62.3637, and its units are in liters times torr over mole K, or liters times millimeters of mercury over mole K. So again, like I have rarely used the last two R constants, but it's also helpful to know them and to just know when to use which gas constant. So this solution is correct. Okay, so I think we have time for one more question. Question 11 just simply asks, what is a diatomic element? So you'll notice that in the word, you have di, which is one of the prefixes that we use that stands for like two of something. So basically a diatomic element, as you can guess, is composed of two elements bonded to each other. So the most common diatomic elements are like the natural, like hydrogen, nitrogen gas, oxygen gas, chlorine gas, and like chlorine. And typically they are non-metals. Okay, so diatomic elements are types of substances composed of two elements bonded to each other. There are only a few of them, 5 of which are naturally occurring at standard temperature and pressure condition, while the other 2 exist at a higher temperature compared to STP conditions. These are all stable molecules at the condition that they are existing. 5 diatomic molecules that exist at STP are hydrogen, nitrogen, oxygen, fluorine, and chlorine. Other 2 are bromine and iodine. This solution is correct. I think I can actually just answer this last. How do you convert cups to quarts? So just basically, there are 4 cups in 1 quart. So for example, if I wanted to figure out how many quarts are in like 24 cups, I would just multiply by this conversion factor. Whatever we're looking for is at the top, divided by 4 cups. The cups will cancel out. And you get like 6 quarts. And our junior tutor said the same thing. There are 4 cups and 1 quart. Okay. So that brings us to the end of today's session. If you like today's Q&A and you'd like to be notified of when we do this next, then please hit the subscribe button and the notification bell below. And if you wanted to submit a question of your own, then check out the links in the description. And also don't forget to leave a like and a comment if you enjoyed today's video. And feel free to send it to all of your classmates and your friends if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.